Welcome everyone. Let's discuss another question from GATE previous year questions. The question is, consider a simple uni-substrate enzyme that follows Michaelis-Menten kinetics. When the enzyme catalyzed reaction was carried out in the presence of 10 nanomolar concentration of an inhibitor, there was no change in the maximal velocity, which is Vmax. So this is a question related with the Michaelis-Menten kinetics, and also there is an involvement of the inhibitor. The other part of the question says, however, the slope of the Lineweaver-Burk plot increased threefold. The dissociation constant for the enzymatic inhibitor complex in nanomolar, we have to calculate. Now, since there are many terms that have been used in this question, let's discuss few of these concepts. So when we talk about competitive inhibition, remember, this competitive inhibitor mimics the substrate for the same active site. And what it does, it increases the Km value. Km is the affinity between the enzyme and substrate complex. But the other thing which we need to understand is, even in case of the competitive inhibition, we can still achieve Vmax. And the reason being is, since at the same active site, both the substrate and inhibitor binds, basically there is a competition. So you can overcome this situation by increasing the concentration of the substrate. So what happens is your Vmax is still unchanged in case of the competitive inhibition if you are making use of a high concentration of substrate. However, this results in the increase in the Km value, and we all know Km is the substrate concentration at which rate of the reaction is half of its maximum velocity, and it gives you the idea about the affinity between the substrate and enzyme. So if there are enzyme, if there is an inhibitor as well as the substrate, there is going to be the competition, and that will result in the increase in the Km value. Why I'm telling you, because you just read this question again and it says that the same thing it says. Why I'm considering the competitive inhibition is the reason being, it says when the enzyme catalyzed reaction was carried out in the presence of this much concentration of an inhibitor, there was no change in the maximal velocity. That tells us that this is an example of competitive inhibition. We all are aware with the different kinds of inhibition, be it competitive, non-competitive, uncompetitive. So this is a perfect example of the competitive inhibition. Now, there are other terms also. For example, Lineweaver-Burk plot. So as we all know that this is the famous equation which we have discussed before, which describes the enzymatic kinetics, and this was given by Michaelis-Menten. And as you can see is, by plotting a graph between the substrate concentration and the reaction velocity, there is an increase in the rate of the reaction, which, eventually gets saturated. And this, with the help of this graph, people have tried calculating the Vmax value, but the value of the Vmax and the Km, which is calculated from this graph, is not generally accurate. The reason being, even at a very high concentration of the substrate, this rate of the reaction is still increasing, although very slowly. So if I have to calculate this Vmax, which is lying somewhere here, I still need to extrapolate this graph, which will not give you the correct value. So what we generally do, we rearrange this equation in a reciprocal manner. So this is the one, this is the same equation. This is the same equation arranged in a reciprocal manner. Both, there is a reciprocal taken both on the right hand side as well as on the left hand side. And this is a perfect example of a straight line equation, y equal to mx plus b. So you have y 1 by v naught, reciprocal of the reaction velocity. Again, on the x-axis, there is a reciprocal of the substrate concentration. And that's the reason, many of the times it is also called as the double reciprocal plot, which was given by Lineweaver-Burk plot, which is also called as the Lineweaver-Burk plot or double reciprocal plot. Now, if you follow this equation, so you have on the y-axis 1 by v naught, m is the slope, and then you have the x-axis 1 by substrate, another reciprocal, and then b is the y-intercept, which you can see here, 1 by V max. Keeping all these ideas in mind, we'll solve our question. But before that, that all these plots were absent, were obtained in the absence of inhibitor. However, since we are dealing with a competitive inhibition, as mentioned rightly, is you have the substrate as well as the inhibitor, and that is going to affect the Km value, but not the Vmax value. And what is happening here is both. Rather, there is going to be a competition between the enzyme, there is going to be a competition between the inhibitor and the substrate for the same active site. And what will happen is that will result in the change in the Km value, which we also call it as a apparent Km value. Apparent Km, which we'll discuss in a moment. And as I've said before, you can still achieve the Vmax. So the Vmax remains unchanged in case of the competitive inhibition, because you can increase the concentration of a substrate to a large extent such that all these substrate molecules replaces the inhibitor from the active site in an ideal situation. Now, this equation is the same equation which we discussed in our previous slide, but in the absence of the inhibitor, this graph is in the presence of a competitive inhibitor. And if you look at this equation carefully, there is a change in the slope. So the slope of this plot is changed by this factor, which I am calling it as an alpha. You just have a look at this equation. 1 by V naught equal to Km by Vmax into 1 by S plus 1 by Vmax, which I am calling it as a straight line equation. Here also you have the same thing, Km by Vmax into 1S. So you have Y m is the slope, but there is a change in the slope of this plot, which is increased by the factor of 1 plus I by Ki, which I'm calling it as a alpha. And that's the reason I'm calling the Km as Km alpha, because we all know in case of the competitive inhibition, there is an increase in the value of Km, and that that increase is represented by an alpha factor, which I'm calling it as a alpha is equal to 1 plus I by Ki. Ki is the dissociation constant of an enzyme inhibitor complex. I is the concentration. Now, keeping all these things in mind, let's read this question once again and try to solve it. So, same thing which we have discussed till now. And what we need to do is we need to calculate the dissociation constant for the enzyme inhibitor complex. Remember, they have given you the enough hint that this has to be an example of competitive inhibition, because there is no change in the Vmax, but there is an increase in the Km value. So what does that tell you? As I said, in this case, the Km apparent is represented by Km alpha, and this much is the increase in the Km value. So, however, the slope, which is represented by Km by Vmax, the slope Km by Vmax is increased by a factor of this much. And this I'm calling it as a alpha, which is represented by 1 plus I by Ki. So alpha value is going to be 3. And then what you need to calculate is the dissociation constant, which is Ki. So the final answer is going to be 3 equal to 1 plus I is given 10 nanomolar. 10 divided by Ki. Rearrange this equation. 3 equal to Ki plus 10 by Ki, and rearranging this equation will give you, so if you all can recall, the previous equation was 3 equal to Ki plus 10 divided by Ki. This will give you 3 Ki equal to Ki plus 10, and hence The dissociation constant is going to be 5 nanomolar. This is what has been asked, the dissociation constant for the enzyme inhibitor complex in nanomolar. So the correct answer is 5 nanomolar. I hope this solution is clear to each and every one of you. If you do have any confusion, feel free to comment in the comment section. Thanks for watching the video.